all modern cars today are basically computers on wheels, and they have an intelligent system that basically monitors the vehicle's health and reports to us if anything goes wrong, which is the onboard diagnostics in full. So in this masterclass I've created, I have basically selected the key points that you need to know to get started working with OBD systems. Whether you're a student, technician, or someone who's interested in cars, this is a very good starting point for you to get started with working on cars and working on the OBD diagnostics. From the network systems you're going to interact with, CAN, LIN, and others, to the different data types, that you're going to interface in the OBD system. We've looked at the OBD architecture. We've looked at everything you need to know. So subscribe to this channel, and also make sure you note out a few points from this masterclass. If you have any question, leave it down below in the comment section, and I'll be answering it when I see it. Okay, have you ever seen a check engine light on your vehicle's dashboard and you wondered what that is? Well, that is a sign that your vehicle is alerting you of a possible fault or malfunction within the vehicle, and this is what we call OBD. OBD in full is onboard diagnostics. Basically, OBD is a system within the vehicle that helps it to monitor the vehicle's health and basically report any faults that have risen. So let's briefly talk about the origin of OBD. OBD basically was introduced in California in the USA, and in the initial stages one of the main roles was to control and monitor emissions in vehicles. So the first set of OBD was OBD1, and in OBD1 we had different car manufacturers, Toyota, Mitsubishi, Ford, and others, having manufacturer specific standards. Each car manufacturer had their own standards. But in 1996, the Society of Automotive Engineers and the International Standards Organizations decided to standardize this OBD system. And basically in 1996, OBD2, the one we are using today, was introduced, and all cars that were manufactured after 1996 were mandated to have this OBD2 system. Now OBD2 basically uses different avenues to monitor faults in vehicles, from sensors, actuators, ECUs, and so on. It basically uses a combination of different components to monitor the vehicle's health and report any faults that the vehicle may have at that moment. Okay, now in this video, let us look at the OBD system architecture. And basically by architecture we mean a combination of different components that basically help the OBD system to function in the vehicle. You can see here the main component of this system architecture is the ECU, and the ECU is the electronic control unit, which is the vehicle's computer. It stores codes, it receives information, it gives out commands, and so on. So basically this is the brain. We also have sensors. Sensors give signals to the computer. Basically sensors monitor the vehicle's physical condition and turn this condition into electrical signals, then feed to the ECU. We can have sensors like the oxygen sensor, the map, and so on. We have car controls, and in controls we can have maybe switching points and so on. We have actuators. Now actuators are like the physical components in the car that basically execute commands from the computer. Sample actuators, we can have fuel injectors, ignition coils, and so on. So basically these ones execute commands issued by the ECU. Then we also have the OBD port, and basically the OBD port allows us to access and read the ECU information. This is for OBD2, it is a 16-pin connector. On the vehicle, you can get a diagnostics machine and connect to this port. Basically, you can read codes, you can give out commands to the computer via this port. We also have a check engine light or a malfunction indicator light. Basically, if there is any issue in the car, the ECU will store a code and also illuminate a check engine light for the driver or for anyone with the vehicle to notice. So these are a series of different components that enable the OBD system to function. Yes, so OBD is not just one component, it's not just a single component, but a series of different components that make up a system. And we also have the network system that is basically embedded in all this system, and the network system basically transports the signals. You know, you can have the CAN, you can have the K line, and so on. So that is the system architecture for you. Okay, so we have looked at the OBD architecture in our previous session, and in this session I want us to look at the OBD data link connector. And basically this is a 16-pin female connector located on the driver's footwell in most cars. And what is the role of this connector is to give us communication to the ECU and also provide power to our OBD machines. So what I want you to do is just understand how this works. Don't just cram the labelings. So just basically understand. So on our connector here, we have main lines, we have communication lines, and then power lines. Simple. So as you can see here, this is how a 16-pin data link connector looks like. And if you check under your vehicle, under the driver's side, you will see this pin here. It is a female connector, meaning that we plug into it. In order to access information from the ECU, we have a diagnosis machine. This is a sample. This is a J2534 VCI for Toyota, and basically if you want to connect, you just plug this into the port like this, and then you've connected to the ECU and you can start reading. We can either have cables, we can have Bluetooth devices, we can have scan tools, and so on, depending. So now let us look at the connector. Let us look at the different lines. Now you will notice that some pins are not marked because they are left out for different manufacturers to decide maybe what communication protocol they want to add on or anything else. So here we have pin 2 and 10. It is a communication line, and its protocol is SAE J1850. SAE is Society of Automotive Engineers, but you don't cram this, but you can just understand. Now this one has a bus positive and bus negative, and this one uses what we call pulse width modulation when it is relaying information. So communication protocol basically means a set of language that the vehicle uses or the ECU uses to communicate within and also to communicate with us on our OBD machines. So maybe let's say Spanish, you know, when you want to communicate, but the language I'm going to use is Spanish. So you can find maybe this is Spanish, and then another one is English, another one is Latin, depending. Okay, so we also have pin 4, which is chassis ground. You can see from here, pin 4 is 1, 2, 3, 4. Here we have chassis ground. We have 5. It is signal ground. Now, what's the difference between chassis ground and signal ground? Chassis ground is the negative of the metal surface of the vehicle, and basically this has high current and so on. Then signal ground is ground that comes from the ECU. Basically, there are some sensitive electronic components in the vehicle that we cannot switch using chassis ground, and these require signal ground because for it has less noise. For example, sensors and so on. So that is the difference between the signal ground. Chassis ground is the ground for the metal surface of the body, and signal ground is basically that cleaner ground coming from the ECU. Okay, so we have 6 and 14, a CAN high and CAN low pins. CAN high and CAN low CAN is also a communication protocol, and this one uses differential voltage signaling to transmit data. We'll look into that later. We also have the K line and the L line. These are also communication lines. Then we also have 16, which is the main power of the connector. So sometimes you connect the vehicle maybe, and the machine may fail to connect. Probably you can inspect, are you having power at 16? Are you having a negative at 4? So this is the connector. So just understand how it works. You can know how to locate it. They are located under the driver's side of the footwell. Okay, let's look at vehicle communication networks. And the reason we are looking at this is because in OBD, network is very important for us to receive information. And basically, a network is like a physical wiring or a physical connection of communication between one computer to another, one computer to a device, and so on. So if communication networks were not there, communication would be difficult, and you would basically not get enough information from the computers. So modern vehicles have many computers, you know. They may have an airbag control module, a body control module, a powertrain control module, an engine control module, and so on. And basically how these modules communicate is what we call a network system. And in most cases, a network system will be physical, you know, physical wires connecting different ECUs and different components to relay information. Now, most common computer networks we have currently, we have CAN. This is controller area network. I'm sure most of you have heard of this. We have FlexRay. We have LIN. This is local interconnect network. We have automotive Ethernet. We have MOST, among others. So in communication networks, I'm going to go deeper into CAN and LIN because almost a large number of vehicles we have on market have this network system. So I'm going to go deeper into CAN and also go deeper into LIN. Now, before I go into CAN, let me talk about communication protocols. So most of you have heard about communication protocol, you know, the SAE J1850 and so on. So a communication protocol is like a set of rules that governs transmission of data along a network, you know, and you'll probably see a communication protocol inscribed as ISO something. ISO is the International Standards Organization. You will see SAE something. SAE is the Society of Automotive Engineers. So these are basically like rules that govern how data is transmitted among all on these communication networks. So let's go and dive deeper into CAN and see how it basically works. Okay, let's see the CAN bus network system. And basically CAN bus network is basically this network system that connects different computers within the vehicle. And as you can see here, we have these different subcomputers. We have the body control module, powertrain control module, airbag control module, transmission control module, engine control module, and so on. So the way the system in which these different computers use is called CAN network. And then these physical wires connecting to the different computers are what we call the bus. So hence the name CAN bus network. So now in CAN bus we have what we call CAN high and CAN low. CAN low, this one, it is the one that has a lower signal reference, voltage signal reference, and then CAN high, it is the one that has a high voltage signal reference. Now the way data is transmitted in this CAN bus network system is called differential voltage signaling. Now let me draw here a simple graph. We have the idle state, and at idle we have 2.5, this is voltage, we have 3.5 volts and also have 1.5. now okay, let me draw here. Okay, let me also draw here. Okay, now you can see we have CAN high, and CAN high is the one that is it rotates from 2.5 to 3.5, and CAN low signals from 2.5 to 1.5. Okay, let me call this CAN low, and this is CAN high. Okay, so at idle state both wires are at 2.5 volts. When they are transmitting data, CAN low fluctuates to 1.5 and CAN high fluctuates to 3.5. So this difference in voltages is what we call differential voltage signaling, and each difference in voltage is interpreted by the computer in binary and carries a message. So this is what basically a simple analogy of what CAN bus does. Yes, another thing I'll talk about is in CAN bus we have what we call resistors. So as you can see on this diagram, we have two resistors here at the beginning of the system and at the end of the system. We have 120 ohms at the start and 120 ohms at the end. So the reason they put these resistors is basically to avoid echoing of the system. See, the system here depends on signals. So if signals travel through the CAN bus wires and end up at the extreme point, if they are not absorbed by this resistor, they're going to come back and basically disorganize our system, and the computer will have wrong readings. So that's why you're seeing these two resistors. These resistors basically can be, maybe they can start in the ECU, they can start somewhere, and they can end maybe in the instrument cluster and so on. So depending, and if you're measuring a resistance in the CAN bus network, the resistance is basically 60. I think as you can see here, if you use the formula 1 over R total is 1 over R1 plus 1 over R2. So if you get 1 over 120 plus 1 over 120, 1 over all of this, your total resistance will be 60 ohms. Meaning that in the CAN bus network system, if you're maybe carrying out diagnosis and you're measuring the total resistance, you must get a value of 60 ohms. If you get maybe 120, it means maybe this the resistance is faulty, or you have a breakage. And if you have a breakage, basically this means that in parallel you've only remained with 120 ohms only. And if you use this formula, you will see that yes, the resistance will be 120 ohms. Okay, so basically this is something brief I have talked about the CAN bus network system. And if you want to physically access CAN bus network wires, you will see when you go to the vehicle, probably from one ECU to another, you will see two twisted wires, and these wires are usually, one of them is CAN high and the other is CAN low, and you can only measure, you can identify which is CAN high and which is CAN low. If the system is active, you can see the one that has voltage that fluctuates between 2.5 to 1.5, that is CAN low. The one that has voltage from 2.5 to 3.5, that is CAN high. So if you've worked on a vehicle and if you've seen these two coiled wires, those are the CAN wires, most probably. Okay, so I think that's what we're going to talk about, the CAN bus network system. And next, let us look at the local interconnect network. Okay, we are going on with our OBD training, and I want to talk about lean bus network. Now, lean is a interconnect. Lean is a local interconnect network, and this is basically one of the most common networks that are used in vehicles. Actually, most cars use CAN and lean in coordination, and lean is basically used for devices that do not require high speed, and also unlike CAN, in lean we are having one single wire in which the message is relayed. Example of systems and devices in cars that use this network can be like doors, mirrors, climate control systems, wipers, and so on. So now, as you see on the diagram, in lean network we have one master node, which can be the ECU or ECM, sending messages to different slave nodes. Now, a master is the sender of the message, and a slave is the receiver of the message. I'll give an example of a system that uses lean is mirrors. For example, we have a master node, which can be the mirror control module. I'm giving an example. So when you press a button to open the rear mirrors, the master node, which is the mirror control module, will send a message to let's say you want, this is 1, 2, 3, 4, let's say you want to open mirror 1, which is slave node 1. So this message will be sent, and the slave node will react to the message. Now, how is the message sent? Now, as you can see in the lean bus, we have one single wire that transmits data, and this wire basically has a battery voltage signal, which is 12 volts maybe, or 24. So basically when you switch, 24 or 12 volts activate in this wire. So basically if you switch on the button for the mirror is going to receive 12 volts, and it will either go up or down. First, it is already grounded. The motor in the mirror is already grounded. Okay, when I talk about the mirror, basically talking about the system which includes the motor. Now the motor here is already grounded. If you press the button and a 12 volts reference is sent to the motor, it will react by either closing, raising, or lowering the mirror. So now this is a simple system. Unlike in CAN bus, this one is less expensive. That is why it is economically friendly to be used hand in hand with CAN bus. the way this one can work in CAN bus is, for example, I can have my, let me say I'm having, these are the doors, okay, the slaves are the doors, and this master node is the door control module. Now the door control module can connect to the body control module, and then the body control module can connect to CAN bus with other modules, powertrain, airbag, transmission, and so on. So that is how Lean can work handy with CAN bus and do the role that we want. Now in OBD, basically Lean helps us to, let's say during actuation, there's what we call actuation component testing. Let's say you want to test if your doors can open. You can do that using an OBD machine, and if you do that, basically the master node will send a signal to the slave you want to open the door, wiper, mirrors, and so on. So that is basically all about Lean. It is just a simple network system, uses one wire. It doesn't have that much speed than CAN bus, and it has what we call a master that sends messages to the slaves. A master sends a message and the slaves react. It can send to all, it can send to one at a time depending on how it was designed to do. Okay, let's continue with our learning, and in this session I want us to talk about OBD data types. And basically, as you're carrying out diagnostics with cars, data is something that you're not going to avoid. So basically, data helps us to know what is happening in the car, what has gone bad, analyze the vehicle's behavior, and basically identify a few things here. So this is something that you should understand so that you can get ways of starting with carrying out proper diagnostics. Okay, so we have different data types, and the first data type I'm going to talk about is what we call OBD codes, which will be called diagnostic trouble codes or DTCs. So these are very common. I'm going to talk about freeze frame data, okay, this is also another data parameter. We also talk about PIDs. These are parameter identifiers. We're also going to talk about readiness, monitors. So these are the most common data types that will interface when you're working with OBD data. And I want us to go right away with the OBD codes and look at them. Okay, let us look at the diagnostic trouble codes, DTCs. Okay, so what are trouble codes? Okay, so if you hear anything like a trouble code or anything, so this is how it is. In a car, we have sensors. Okay, we have sensors, we have the ECU, and we also have the check engine light. Okay, now sensors in the car help you to monitor the vehicle's health. If a sensor detects an abnormality, it's going to report to the ECU. So the ECU will throw a code, will store a code, a diagnostic code, and will also illuminate a check engine light. So basically, a trouble code is a code that signifies a specific issue or problem within the car. It's like a form of the ECU reporting to you about what is not going okay in the vehicle. So that's what basically a trouble code is. And we have different trouble codes. We have codes starting with P. We have codes starting with B. We have codes starting with C and U. Now codes starting with P are those to do with the powertrain. The powertrain is basically the components that give power to the vehicle. For example, the engine, transmission. We also have the body. So here the body, we have things like the seats, you know. We have the chassis, and the chassis is basically the frame of our vehicle. So components here we can have the suspension system, you know. We have U, and U is network. So this is where you'll see CAN bus codes and so on. So if you say code is starting with the P, it is to do with the powertrain, B body, C chassis, and U network. Okay, so let me give you a sample code. Let's say P0302. Now this one, this is a powertrain code, of course, because it's starting with the P. This basically signifies misfire detected in cylinder 2. So this is what this code means. So I want us to look at the basic structure of how this code is made. So the first letter here is the main system. You can see powertrain what. Then the next letter here, if it is 0, this is generic. Generic means that the code applies to all cars. If you have a code that has 1 instead of 0, so you have like P1 something, then 1 is manufacturer. Okay, for example, Benz may have their own code, and we'll say a code like P1 something. So if you see any code like P1 something, then you're dealing with the manufacturer's code, Toyota, Benz, and so on. Okay, then the third letter here is the system that you're diagnosing. For example, for this very code, 3 is representing the ignition system, where we are detecting these misfires, and then the last 2 letters here point out the exact issue or exact location. For example, here 02, we are basically telling us that the misfire is detected in cylinder 2. So this is the basic structure of a code. Okay, so I want to also talk about the diagnostic trouble codes. They're what we call current. Okay. We can have current codes, or you may call them stored. You may have pending codes, and we also have history codes. So what do these all mean? If you see any current or stored codes, these represent a current issue that is happening within the car. If you see pending, sometimes the sensors monitor an issue and send the data to the computer, but the computer may not exactly rule it as an issue. Sometimes the computer is always monitoring before it rules out the issue. So for that case, you will see a pending code, and in some cases a pending code may or may not bring a check engine light. Okay, then we also have history. So history codes, these ones are like codes that happened some time back, probably they were fixed, so these ones should not worry you. The type of codes that should worry you are the current, stored, and the pending. Yeah, so if you're having a machine, you probably see current codes, stored codes, and so on. Okay, so we've looked at diagnostic trouble codes. I want us to look at freeze frame as our next data parameter. Now, what is a freeze frame? Basically, if something wrong happens within the engine or within the car, and an OBD code or diagnostic code is generated, the computer captures live data, or how can I say, it captures the live performance of the vehicle at a time an OBD code was generated. For example, if we have that code I've shown you, P0302, it is showing us that we're having a misfire on cylinder 2. The vehicle may capture data that happened. For example, it may capture the coolant temperature at the time this code was got. It may capture the MAF readings, you know. It may capture the map readings. It may capture the battery voltage and so on. So now, if it captures this data that was present at the time this code was developed, this is what we call the freeze frame data. Why do we need freeze frame data? We need freeze frame data basically to analyze what was happening within the engine or within the car when the problem occurred, you know. At the time of this code being developed, was the car moving? Was it stationary? What was the battery percentage? What was the RPM reading, and so on. So basically, freeze frame is to help us analyze basically what caused or what was happening when the issue was formed. So basically, this one is like a snapshot or a screenshot of live data at a time an OBD code is generated. So basically that is what we call freeze frame. And for this data, we basically interact with this data a lot, from analyzing and so on. So that's what we call freeze frame. Okay, another data type I want us to look at is PIDs. PIDs, we can call them parameter identifiers. Now PIDs and OBD are like the different data types or different specific data types that the engine generates, and usually these data types have readings. They have units of measure, you know, percentages, degrees Celsius, you know. For example, sample PIDs we can have, let's say coolant temperature. This is a parameter identifier. It also has an SI unit, which is the degrees Celsius. You can have engine speed, okay, and this can be measured in RPM. We can have battery voltage, and this can be measured in volts. Okay, we can have what else? We can have MAF. We can have the MAF readings for air entering in, and this can be measured in grams per second. We can have the engine load, and this one is basically measured in percentages. There are many parameters. So these PIDs are usually data types generated by different sensors within the engine, and they usually have these SI units. So basically PIDs are like different annotations of data that is being captured from the different systems within the engine, as you can see here. And we need to know this because these are some of the PIDs that the PIDs are the data that we look at if you are looking at the engine performance. Let's say you are in live data. If you are in live data, basically you're going to be monitoring these PIDs. You know, what is the coolant temperature, what is the engine speed, what is the battery voltage, and so on. So basically that's what we call the PIDs. Let me talk also about readiness monitors. Okay, readiness monitors. Now the engine or the vehicle performs what we call self checks on crucial systems, you know, like the evap, the EGR system, oxygen sensors, and catalytic converters, and some other critical systems. So the readiness monitors are like self checks that the ECU does on some of our critical components in the vehicle, basically monitoring their health, checking if everything is okay. So if you're monitoring readiness monitors, you probably see critical systems, especially those to do with emissions being tested, you know, the evap, the EGR. So if something's wrong with them, we'll probably see maybe the system is not okay. You know, if it is not allowed, this your vehicle does not have an EGR system, and so on. So these ones are like self checks done on crucial emission systems within the vehicle to basically analyze if they are okay or not. Okay, let's look at OBD modes. And in OBD, a mode is like a request that tells the ECU what kind of data we need using a scan tool. And the standard OBD modes are 10. You can see them here, and they are denoted by a $sign here. If you ever see anything denoted by the $sign, just know that you're dealing with hexadecimal numbering. And in hexadecimal numbering, this is a numbering used by computer systems. The numbering is based on 16 numbers. We have 1 to 9, and then A to F, where A represents 10, B represents 11, C represents 12, up to F to make 16. So if you see a $sign on any numbering, it means that that is a hexadecimal numbering. And the numbering is like this because we are dealing with the OBD system, which deals with ECUs or computers. So basically the computer can either use binary or hexadecimal. So that's why you're seeing the $sign. And I told you we have 10 modes, 01 up to 0A. And hexadecimal, 0A is 10, like I've shown you here. A in hexadecimal is 10. Okay, so now in the different modes of OBD, we are basically requesting the ECU to give us different data. For example, in mode 1 we request for live data, and if you're using a scan to live data, is that real performance or real time performance of the car, you know, the current coolant temperature, the current battery voltage, the current MAF reading, and so on. That's what we call live data. Then in mode 2 we have freeze frame data. We've already seen this. This is like a screenshot of a live data that was captured when a diagnostic trouble code is generated. In mode 3 we are basically requesting for trouble codes. In mode 4 we are clearing. So every time you finish diagnosing and you fix the issue, you can go on to clear the codes. So that is mode 4. And in mode 5 we are requesting for oxygen sensor test results. Oxygen sensors in vehicles help us basically to monitor emissions, monitor how the engine is performing in relation to the fuel system. Okay, we have mode 6, which is providing tests for monitored systems. These are like the readiness monitors we talked about, you know, those ones that monitor the evap, the catalyst system, and so on. Then in mode 7 we want it to issue to display for us the pending diagnostic trouble codes. Pending diagnostic codes are those codes that the issue stores when there is an intermittent or there is an issue that is kind of a problem, but the issue has not finally ruled out the issue as a current trouble code. Okay, we have mode 8, which is component activation. Now this component activation is used to test different components. For example, you can test starting the car, you can test opening windows, you can test the pump, fuel pump, if it is working, just by using your OBD machine. So that's what we call component activation. Then mode 9, we are requesting VIN and vehicle information. So some machines have what we call an auto VIN feature, whereby when you're connecting, the scan tool will automatically scan the vehicle's VIN and automatically connect to the vehicle. Then we have mode 0A, which is mode 10, that requests for permanent DTC. That is a brief look at the different modes of OBD, because you're going to be interfacing with these modes, and one time you will see mode 4, mode what, so you wonder what is a mode. A mode is just a service request we make to the ECU to display for us given amounts of all given data types using a scan tool. Okay, so I want us to look at mode 1. I'm going to put more emphasis on mode 1, which is the live data, because mode 1 is one of the most key modes in OBD, which is live data, because live data is very important when you are carrying out diagnostics, because as a technician or as someone who is on the vehicle, you need to understand live data so that you understand the performance of your vehicle's engine or your vehicle's different systems. Okay, let's look at live data in OBD, and it's mode 1 of the different modes of OBD. So in mode 1, we are basically requesting the ECU to display for us the live data of the vehicle. So what is live data and why is it important? In OBD Diagnostics, live data is like take it as how your body is at the moment. You know, what is your blood pressure, okay? What is your heart beating rate, and so on. So in live data, we are basically looking at how the vehicle is performing at the current time. You know, how much air is it letting into the manifold, you know, at what speed is it is the engine rotating, you know, at what voltage is the battery at, what is the short-term fuel trim, what is the long-term fuel trim, and so on. What is the coolant temperature at the moment. So this is what we call live data. And live data, and in live data, a key point when we are carrying out diagnostic is you have to know the normal, range, and the abnormal range. I'm talking about this because when you're monitoring live data, you're basically looking for inconsistencies in data. I'll give an example about coolant temperature. If a car has been warm for some time, the coolant temperature must be between about 85 to 105 degrees Celsius. So this is the coolant temperature of a perfect engine that has been warm. So if you're observing under live data and you're seeing your temperature within this range, this is the normal range and you consider it okay. Then abnormal range is when your engine has been running for some good time, let's say 30 minutes, let's say 40 minutes, 1 hour, but you're observing your coolant temperature as 40 degrees Celsius. Now this is a red flag. So this is how live data is helping us. We are noticing that the engine has been on for 1 hour, but it is throwing an improper value. So in live data, we are looking at inconsistencies. We are looking at what is not functioning properly. Meaning in live data, you have to know the different PIDs. The different PIDs like sensor data, different sensor data, different parameters, and for the different parameters, like I've given an example of current temperature, you have to know what is the good range, what is the bad range. For example, I'll give an example with engine load also. Engine load is measured in percentages. At normal, the engine load at idle, the engine load is about 10 to 30%. So this is when the engine is not in stress, it is at idle. But when you apply the throttle, when you're driving, the engine load will go up to 100%, depending on how much power you're giving to the vehicle. So all this is monitoring, meaning if you're giving 100% throttle to the vehicle and you're observing it having an engine load of 10, 20, that means there's something wrong. So this is how live data helps in OBD for us to monitor different key parameters and basically be able to rule out what is wrong and what is not going on okay. Okay, so there are many different types of data we are going to observe, but specifically, let me talk about some of the common data types, and I'm going to talk about basically the fuel system, and I'm going to talk about what we call the short-term fuel trim and the long-term fuel trim. It is something that I want to put on emphasis because these are the key components that we usually use when you're carrying out diagnosis in vehicles. Okay. Okay. Let me talk about fuel trims. So what are fuel trims? Now, in a vehicle, we have different sensors that help the ECU to deliver fuel to the engine. And the ECU uses different sensors, the oxygen sensor, the MAF, and many others to basically determine how much air or how much fuel to be delivered in the engine. And this is all performed in order to maintain the stoichiometric ratio. And the stoichiometric ratio is 14.7 to 1. And this is the ratio of air to fuel in an engine, meaning in an engine you need 14.7 grams of air and 1 gram of fuel to make a perfect fuel air mixture that will give you the optimum power. So now the engine always, the ECU always tries to maintain or tries to achieve this ratio by trimming fuel. And trimming fuel is basically deciding how much fuel is being delivered to the engine depending on how much air is there. So that's what we call the trim, the trimming or the fuel trim. Now when you're in live data, you're going to see something like short-term fuel trim. Okay, now short-term fuel trim, this one is like the continuous trimming of fuel. Means that the engine is, the issue is always using sensor data at every moment to trim, and the short-term fuel trim basically ranges from plus or minus 5. This is the range. That means under live data, you see the short-term fuel trim ranging between -5 to 5. When you say negative in trimming, a negative means that fuel is being reduced. A positive means fuel is being added. So if you see a +5, it means that fuel is being added. If you see a -5, it means fuel is being reduced. If you see a -3, fuel is being reduced. Now, that is what we call a short-term fuel trim. Let me also talk about long-term fuel trim. And basically, long-term fuel trim occurs after you've been driving for some time and the engine is normalizing the sequence. For example, if you've driven for 1 hour and the ECU is positively trimming, maybe it is slightly leaning to a positive trim of maybe +2, +2. Now, in long-term fuel trim, the long-term fuel trim is like going to be the average of how your short-term fuel trim has been. If you've been mainly getting positive trims, your long-term fuel trim will be also a positive or slightly close to the short-term fuel trim. So like an average of how your short-term fuel trim has been performing. And the good range of the long-term fuel trim is usually between plus or minus 10. And it is also the same case. If you see a positive long-term fuel trim, it means that we are adding fuel. If you say negative, it means that we are subtracting fuel, or we are reducing the fuel being delivered to the engine. Now, for you to understand fuel trims, you need to understand something called lean and rich. These are some of the terms that you will basically come across. So what is a rich condition? What is a lean condition? Now, in a car, like we've seen our fuel ratio here, which is 14.7 grams of air to fuel. If there is more air than fuel, that is a lean condition. So in a lean condition, we have we are having more air, less fuel. More air and less fuel in the engine in relation to the stoichiometric ratio. Then in a rich condition, we are having more fuel, less air in relation to the stoichiometric ratio. So this is what we mean. If someone says your engine is rich, it means that it has more fuel than the air inside. They are not balancing. If it is lean, it has more air than the fuel inside. So, for example, in trimming, if your engine is rich, if it is having more air, the ECU is going to correct this by giving you a negative subtraction. That means you'll have a negative trim, which means the ECU will trigger a reduction of fuel delivery. If your engine is lean, if it is having more air and less fuel, you will have a positive trim, meaning that the engine will increase the amount of fuel to match up with the air that is within the engine. So let me go back to fuel trims. Let's say you're having a positive 20 long-term fuel trim. Now positive 20, this means that we are having a high lean condition in the engine. A high lean condition in the engine, meaning we have a lot of fuel in the engine. So meaning that we're having an abnormal fuel trim that was triggered to correct this condition. So if you're viewing the live data and you're looking at the long-term fuel trim and you observe it is positive 20, so you have to analyze that what causes this excessive air to enter into the chambers. Is there something with the mass airflow sensor? Is there something in the inlet? Is there, which other values am I seeing that are abnormal? So you have to investigate. If you're having like negative, let's say 18, this is a rich condition, meaning in a rich condition the ECU tried to reduce the amount of fuel by correcting negatively to match up with the air fuel ratio. So also observe, why is my engine too rich? Why is it delivering too much fuel? Is my fuel pump okay? Is it delivering the right amount of fuel? Am I getting sensor values okay? And so on. So this is what basically I can talk about the fuel trimming. Another thing I should talk about with the fuel system is a closed loop and an open loop. This is also something that you're going to usually see in live data fuel system, either it is in open loop or in closed loop. So what do these two mean? Now, like I've shown you this trimming here. If a vehicle is using sensor data to trim the fuel, that is what we call a closed loop. In a closed loop, a fuel delivery basically and entirely depends on feedbacks from different sensors, so that the ECU can trim the correct amount of fuel delivered to the engine. And then in open loop basically means that there is no trimming and there's no sensor, there's no oxygen sensor or other sensor data that are helping with fuel delivery. Open loop basically means that the ECU is trimming using the pre-existing maps in its memory. So open loop usually occurs when you just at cold start. Now at cold start, you don't have the right temperature to operate. For example, the oxygen sensors need to operate at high temperatures so that they can start giving feedback. But at low temperatures, at cold start, your system is going to be in open loop. So if you're in live data and you've just started your vehicle for maybe 1 minute, 30 seconds, it will show you open loop because the feedback sensing has not kicked in. But if you've driven for 1 hour and you're seeing your vehicle still in open loop, there's a problem. If your engine is warm, you've been driving for some good time, it should be in closed loop, because this is when the sensors are giving feedback so that the ECU can trim the right amount of fuel. Okay, so this is a sneak peek of some of the most common live data that will be interacting with in OBD. We shall continue to see different data analysis in future when we get into the details of each sensors. We shall be looking at what is the normal value, what's the abnormal value, and what does each value range mean. In this video, let us talk about scan tools and diagnostic machines. So as a beginner, what is a scan tool? What factors should you consider before getting started working with the scan tools? So first of all, scan tools are basically machines or interfaces that enable us to access information from the vehicle. Whenever you want to read out faults from the vehicle, you should have a scan tool or a machine to access the vehicle. So we have many types of scan tools, many types of machines, and right here I have a sample of this diagnostic machine here. It is an X tool. I love X tool because it is one of the most friendly companies that are making diagnostic machines. Now this one, you basically connect a cable to the car and then you can view data from the vehicle on this interface. I also have some sample cables here. Now for these cables, these ones use the PC softwares where you connect to the vehicle and then you have special software on the laptop where you connect to the laptop and also read some codes. There are some other machines which are smaller, like the smaller OBD machines, which all have a screen interface where you connect and read. We also have Bluetooth dongles, whereby you connect a Bluetooth device or a Wi-Fi device, and then you can use any interface. Let's say your phone, a laptop, a tab, depending. So anywhere you connect to the vehicle, as long as you have an interface that reads, you can access the vehicle's information. So what do you consider when choosing a diagnostic machine? First of all is the cost. You'll find out that most cheaper tools do mediocre work, and this I mean that cheaper tools are basically view only diagnostic trouble codes, and these are limited to OBD2. They are limited to only engine systems. But more expensive tools enable you access data from different modules of the vehicle. The airbag, ABS, the doors, and so on. So for professional grade machines like this one here, these ones can access the vehicle's entire system, and basically if you're diagnosing anything on a vehicle, as long as it is electronic, you can enter into that system and make your diagnosis. But cheaper tools you will not. So that's why I'm telling you, sometimes the cost determines. More expensive, the more expensive you go, is the more functions you will be getting from a machine. Now we have many companies that are manufacturing machines. We have Hotel, X2, Topdon, Thinker, and many. So all of them are good, but my favorite for now is X2 and then Hotel. Why I'm saying X2? Because their interfaces are good on all the devices I've interacted with, and also it is cheaper when you're renewing a subscription. Remember, if you're using a diagnostic machine, they give you a free period. For example, X2 gives 3 years, and after 3 years you have to be paying a subscription for upgrades. So X2 subscription is a little cheaper compared to some other tools like Hotel or Launch, and depending on the functionality, you find that they're doing the same work, but this one is less expensive. So that's one of the reasons why I like X2, is that they give you a good service and at a lesser price. Okay, so we also have manufacturer level diagnostic tools. For example, Toyota has what we call TechStream. This is an example of a VCI. It's a J2534 cable. It is for Toyota. It uses the Toyota software, which is called TechStream. So now different manufacturers have different softwares they created specific for their vehicles. Like Toyota has TechStream, Benz has Zentry, and other different cars. So you'll find out that if you're using software from a manufacturer, you will be able to get more functions and more support if you're using a manufacturer's software than when you're using a general machine. Yes. And the other thing you may consider is the advanced functions. In advanced function, we have what we call special functions in these machines. Special functions like battery matching, injector coding, throttle relearning, EGR relearning, and so. These special functions differ depending on the different type of device they manufactured. Meaning, if a device has more special functions, it will also be more expensive. Yes. Then we also have the issue of brand coverage. Most diagnostic machines, especially those manufactured in Europe, will tend to have more coverage for European vehicles than Asian vehicles. And you find out that the more a car has, the more a machine has more coverage, the more expensive it may become. And then you may find that if a machine has been manufactured from Asia, you'll find out that it has more compatibility with Asian vehicles than European vehicles. So brand coverage also matters depending on the type of machine you're having. But all in all, as long as you have a vehicle that has a communicational, that has a protocol that can communicate with your vehicle, as long as you can access your vehicle and communicate with the ECU, you can do all kind of diagnostics.